Okay, chapter 2, modeling in frequency domain. Chapter 2 is about the Laplace transform. So we're going to model in the system in the frequency domain. What does that mean? We'll talk more about it. And in this chapter, we're going to talk about the Laplace transform, and then we're going to talk about transfer functions and find the transfer function in the circuits, and then translational mechanical system and rotational mechanical system. Those are the three different systems that we're going to take a look at it. Input and output. So again, this is the diagram, and we're going to set R of t as an input and C of t as an output. R stands for reference the input. C stands for controlled output. Okay. I'm not going to repeat this in the later. So when I said you need to find the transfer functions, which is output over input, that means in the equation, you need to find C of t over R of t in the time domain, frequency domain, C of s over R of s. And transfer function in the frequency domain is we're going to talk about today. And then state equation in the time domain, we'll come to that later. Let's talk about the Laplace transform. You saw this Laplace transform in your A Math 1 the first time. And then you had the signals and system, then probably you saw there as well. So the Laplace transform definition is going to go from negative infinity to the positive infinity. However, we're going to consider only positive side in this class. We call unilateral Laplace transform. So we're going to have a 0 to infinity f of t, whatever the time function, we multiply by e to the negative st. S in here is a j omega. Okay? So it is in the complex number. And inverse Laplace transform, by definition, is going to be 1 over 2 pi j integral this. So this handout covers all the equations in chapter 2. So when we have quiz exams, I'll give you a new sheet of this equation sheets. Anything on here, you don't have to remember, but you need to know how to use them. So this is the Laplace transform pairs. So delta u, tu of t, t to the n, e to the at, sine and cosine. We're going to use all of this, all 7 of this in this class. And the second table, you need to know the definitions and the shift theorem, and then differential equations, and then final value theorems that we're going to getting into later chapters. F of t is given a times e to the at, and using Laplace transform definition to find f of s. So we just need to plug f of t into the definition, right? So if we do a e to the at times u of t times e to the negative st, and u of t, what is u of t? So unit step function. This is u of t. This is 1. Everything less than 0 is going to be 0. Anything greater than 0 is going to be 1. If we have a u of t multiplying in some function, just making all the e to the at graph, only we take larger than 0, right? So only positive side. And we can combine e to the at and e to the negative st. Take the negative out, combine them together. A is the constant we can take out. And then u of t again, multiplying any function, will tell us from 0 to infinity. So there's nothing effect on u of t in here. And then if you take the integral of this guy, it's going to be a over negative a plus s. And then we put infinity and 0. And that is 0 minus 1. So it's going to be a over a plus s. Now, let's find the inverse Laplace transform of this guy. Copy this down. F of s is given as 1 over s plus 3 squared. Without using the inverse Laplace transform definition, we're going to only use these tables to find inverse of that guy. From table 2.1, we have Laplace transform of t of u of t is 1 over s squared. And from table 2.2, for translation theorem, e to the at times f of t is f of s plus a. Dr. Kim, there is pair e to the at. When you take the Laplace transform of e to the at in the table, it's going to be table 2.1, number 5, e to the negative at 1 over s plus a. But here, table 2.2, number 4, this is this. So if you have e to the negative at, e to the power of something t itself, then that's true. But if we multiply e to the power of something to any given function, that e to the at is going to be translating the function by a amount. So we're going to use these two. They're right here. So e to the negative 3t, f of t is going to be f of s plus 3. Now it is a square term. So it's going to be e to the negative 3t times t times u of t. Partial fraction expansion. Please make sure you understand this partial fraction expansion and work on the homework problem. We're going to use this for chapter 2 and the first quiz and first exam and the final exam. There are 3 different cases in the partial fraction expansion. I want you to pull out your calculator. We want to see whether we can factor this out. So using your calculator, it's a second order polynomial. You can find the root using your calculator. Find the roots. The root is going to be -1 and -2, right? If this is the case, we can do a over s plus 1 and b over s plus 2 and find the value of a and b. However, sometimes it's not going to be factorable, something like that. I want you to try this. Using your calculator, find the roots for me. You can do the partial fraction a over s plus 0.31 and b over s plus 3.18. Find a and b. So the first case, roots for the denominator, they are real and they are different. Then we can do the partial fraction, something like this. Now in the case number 2, there's a repeated roots. Going to be a over s plus 1 plus b over s plus 2 plus c over s plus 2 squared. You can also do, when we do this partial fraction expansion, numerator always has to be 1 degree less than the denominator. So we have as plus b over s squared plus c over s plus 1. So numerator 1 degree less. If the denominator is s cubed, then numerator has to be square terms. Now, for this guy, okay, the square term, I can separate this. Then what's going to happen? As over s squared plus b over s squared. Okay? And then the first term, s and cancel, a over s plus b over s squared. So we're going to apply same technique in here. So we have a square term at the denominator. Instead of doing this, we can do b over s plus 2. And the third term, the c over s plus 2 squared. Because in here, s and s cancel out just like what we did. Why this is better? Because if we have something like this, if you look at the pairs, the inverse Laplace transform, the numerator, they are all constant except for the cosine. For the cosine pair, we have s over s squared plus k squared. And the denominator, there is no s terms for the cosine. All others, the numerator, we're not going to have any s. So if you do this, you end up getting into this form. Otherwise, you won't be able to do the inverse Laplace transform. But this, if you do this, it requires like a 3-4 more steps than this guy. So instead of doing all of case 1 and 2, I'm going to do this one. It has everything. So let's do that. Copy that down. And if you're trying to find the root for the denominator, s squared minus 6s plus 14, your calculator says no roots, give you error. Why? Because b squared minus 4 times a times c is less than 0. That means complex number. So we don't have the real. To get the partial fraction, we need to do a over s plus b over s squared plus cs plus d over s squared minus 6s plus 14.